Hi, my name is Keye Martin. I can't be at the conference this week, but I wanted to thank Bob and the other organizers for filming me here, right, so that I could give my talk and you could hear what I had to say. So it's called The Mechanics of Information, and what I mean by it is literally what it sounds like, which is, that in classical physics you have this part of, the world we study called classical mechanics, right? And so what you do is you say things like this. You say, well, the sum of the forces that act on a body, are proportional to the acceleration, right? It's like one of the laws. Now, I want to be clear about two things. So the word kinematics really just refers to the math that you use to describe the motion of things. But the word dynamics, I think of as more physical. Dynamics means the stuff that allows you to derive the trajectories, right? So that would be like this. Now, so this talk is about the dream of a mechanics of information, right? What I'm going to show you is how we have the kinematics of information, right? And how it actually has applications to things in computer science. But we don't have any clue about the dynamics of computation in this context, right, that I'll be talking about. But I just went ahead and named the paper this because I really like the way this title sounds. And so if somebody does one day discover the mechanics of information, I just want to be able to say, well, it doesn't matter because I already took the title, so go to hell. All right. So the kinematics of it, right? The idea is this. You're interested in processes or in algorithms or whatever, right? And they move in an informatic space. The space is described by an order-theoretic object called a domain. So it's a collection of informative objects, and you have an information order, and the order means this. If we write this, it means X carries information about Y. This is a qualitative view of information. Now, we have these functions called measurements, which in the paper I call variables. And that's to make the analogy between what I'm talking about here and, ordinary mechanics from physics closer. This is a variable. It's a function. And we'll denote it by V. And it has a few properties, right? It measures uncertainty. So if we say X is below Y, it means that the quantity of the variable, whichever one that we care about, should decrease. And it has a property like this. If X is below Y and the values are equal, then they should be equal. And then something that's also very reasonable. If you have a sequence of things that increase in the order, like here, so X1 is below X2, is below X3, they should go somewhere, right? And that somewhere should be a limit, which we denote by this. It's a soup. And this should be preserved. Now, functions like this abound throughout physics and computer science and information theory. So some really quick examples are Shannon entropy of finite probability distributions, the von Neumann entropy of a density operator in quantum mechanics, global time functions in relativity are like this, and many, many other examples. Almost none of those, except for entropy, will help us today. But this is the basic setup. So here's the idea in a nutshell. We have a qualitative notion of information. We have something that tells us about a quantitative idea. And using just this, okay, what we can now do is completely rip off single variable calculus. We can just reformalize it. If you think about single variable calculus, and people always think about calculus as a single variable, right? And they say, well, take the derivative with respect to the variable. Well, that's the reason I call this a variable, because the first observation is that all of the theorems of single variable calculus extend, where you replace, the infamous variable with a function that has these properties. Then you can prove all the same things. And what we literally want to do is then say, we will have a trajectory moving through this space, right? Except it's not like, through the sort of ordinary spaces that you encounter in mechanics. It's going to be through informatic spaces, so it'll be very, very general, right? And so that's why we have to be explicit about what our notion of variable is, right? So let me show you an example now of how this will work. And this started off, by the way, as a giant dream of mine. I just I wanted there to be a mechanics of information, which meant, mechanics not just like in ordinary state spaces from physics, but in really general spaces. So there's a trajectory, right? It's some function, right? And in addition, we'll fix some variable, like we already talked about. And the parameter there is time. We'll think of it as time. And right away, if we want, we can define the time derivative, right? And some strange things happen, but they're very beautiful. So here's one. See? This is the first time derivative of the trajectory x with respect to the variable v. Because there are many variables in this domain, right? And then how do we get it? Well, we look at the value of the variable, and then we divide by the difference in the times. You see? And it just, and you get something nice here. And then you can go on literally with this definition. And by the way, the second derivative is even easier. Because once you take the first derivative, you now have a real valued function defined on times. So its second derivative is just literally, the normal second derivative. So this is the only one we have to even think about. But once we do this, we get these sort of things. So let me show you a couple of things that follow, like really quick, right? Suppose we have a trajectory named x, right? And we want to know, when is it monotone increasing? Right? So this means that it moves up in the order for all points in time. And by the way, we're going to literally start drawing things like this in a minute. So this is going to be the time axis, and this is what we're going to call, the less than or equals to axis, right? If we move up, we made this up, right? But as time advances, we move up in this order. And so we can prove things like this, right? X is monotone increasing if the first derivative here, right, is always, less than or equal to 0, and the image of X is a chain, right? Which means that any two elements compare. Now, see, the reason, by the way, this looks opposite to calculus is because, remember, V is a measure of uncertainty, right? As you move up in the order, right, it decreases. So what this says here is that uncertainty is decreasing as a function of time. See? And if uncertainty is decreasing, then it must mean that you're moving up in the order, right? So the conventions are opposite to this, right? To what we're used to in calculus. And then we have a similar result for decreasing, right? And then there's one, for a constant function, which is where the time derivative is 0, right? So we have that. In addition, we have things like, here's another one, right? So for all the trajectories that you'll encounter in physics, in any realistic situation, here's what happens, right? There is a point in time named t star, where if you look at the value of the trajectory, it will actually be the soup of all of these things, right? So that's the first thing. And then the second thing is, how do you find this t star? Either when you take the derivative, this thing is 0, or it does not exist. All right? And what I want to point out is just like the last result I wrote, and this one. This is independent of the variable. All right? This is a very absolute statement right here. Right? This statement says, all right, if you have a trajectory that you're graphing, all right, there's some place, and the details are in the paper, but there's some place where it assumes its largest value, right? Like maybe right there, right? That's its soup. And that soup is actually attained at this point in time. And how do you find this point in time? Well, for any variable you pick, it doesn't matter which one. Either its derivative will have to be 0, or it won't exist. Right? And it's this part right here, right, that makes this incredibly powerful, all right? Because I'm going to show you now 3 examples of trajectories that arise in computer science, and the role of quantum mechanics in generating these will be clear. But we'll see in particular in the quantum case that the choice of variable is very important, right? And it's counterintuitive, but what we'll see is that choosing entropy as your canonical variable is a really bad idea, because you get math you can't do. Right? And the equations are so ridiculous that I won't even write them down. But then there's a much simpler choice you can make that'll clear things up. Anyway, this was always the idea I had, right? So a trajectory in an informatics space and just, the mechanics of information, right? Very general, beautiful thing. And the only problem with it was that every time you looked at an example, like every example, basically they all sucked. And the reason was because every graph that you picked would always increase. And that's it. Like it would just go like that, or it might be a picture like this. You know what I mean? But there was nothing interesting. You see what I mean? But, we wouldn't really care so much about calculus if everything increased, would we? Nothing like this is what I'm saying. You couldn't find a natural example that was like that. You see? So, there would have been no reason to have any of the basic techniques of calculus, such as, how do you find the maximum? Well, it's the point where the derivative is 0. So you don't need that if that's all you have. So what I found was that computer science has a nice example that's very much like the physicist example of the harmonic oscillator. So in any science, it doesn't matter which one it is. We all take an example. It's simple, all right, but it's sort of complicated enough that you can say something about it, all right? So one of the physicist's favorite examples is the harmonic oscillator. And I found that the problem of searching, right, when taken in a really broad context, is just like what a physicist calls the harmonic oscillator. And I mean that in more ways than one. Not just that it's a non-trivial example that's simple, but that they literally obey the same differential equations when you broaden your idea about these. So let me show you one of the examples that I did not like. So this is linear search, okay? So, in linear search, you begin with a list. Right? And you just go 1, 2, 3, 4, and you just keep searching everything, and that's all you do, right? So let's use the simplest possible model we can find. And the simplest one would be like this. As your domain, you take this, the numbers from 0 to n. And as your measure of uncertainty, right, you take this one. And so what this means, and then by the way, the trajectory, let me just write it now. The trajectory here is this, right? And this is just brain dead easy. So it looks like this, right? And what it means is this, right? Okay, at time 0, my uncertainty is n, because I have n things to check. And after 1 unit of time, I have n minus 1 left, etc. All right? And then the trajectory is just tracking what you've checked. So at time 0, you track nothing. At time 5, you've checked 5 and everything before it, and there's the graph. Right? And in this case, literally, we're on a domain that are numbers, so that the picture satisfied. And like I said, this sucks because it's just straight. Right? There's nothing for us to study here. The next example is binary search. So binary search can be modeled in a lot of ways. I modeled it in a way that's familiar to domain theorists. And so the domain we use here is the collection of intervals of the real line, and they're ordered by reverse inclusion, right? So this is reverse inclusion, and that's defined in the paper, but all it means is that if you have an interval here, you move up, right? Intervals get smaller, right? Now, how do we actually get a trajectory? So this is the first interesting example, I think, right? Because, well, for a couple reasons, but let me just write out something first. So what I'm writing out now is a numerical method, okay, called the bisection method. And there's a well-known correspondence between the bisection method and the binary searching of lists, all right? So I take any interval at all, and then, what do? I go left if some function that I've been given, changes sign. So if f changes sign on the left. So this f, right, is some real valued thing, right? And it crosses the axis somewhere, like here. And this is A, and this is B, and we're trying to figure out where this thing is. And so we go left if f changes sign on the left. And otherwise we just go to the right, okay? Now, see, if you look at this is completely discrete, right? This is just, we'll iterate this. So all we have are discrete times, 0, where we haven't done anything, 1, where we've applied this process once, twice, where we've iterated this function twice, 3 times, and on, right? We don't have a trajectory, right? And this is actually one of the really interesting math questions that underlies all this, which is, how do you get a trajectory like this, right? But let me show you now. In this case, you can. I have no idea why. It's an obvious open question, which is really, really interesting. But I just want to show you that it just so happens that this always works, right? And I don't know why. See, so if you look at this thing and we were to iterate it n times, all right? So that's our input interval that we just call x now, right? It's going to obey this equation. You iterate n times and you split it up like this, all right? And the idea now, right, is to say substitute in for n, substitute t, right? And there's a reason why. Because first of all, it actually has a canonical extension. And so here's what I mean by this, right? You know, we can define some element named x of n to be the nth iterate of this interval, all right? And then, if we're given like a t, say, right, which is not an integer, right, somewhere in between, then it just turns out by like pure magic, all right, and I don't know why, that there is a unique element that we call x of t, and it lies between these two, right? So that's a qualitative thing, all right, and a quantitative thing, which is that its measure, which is its length, I should call this one an AB, because that's going to be really bad notation. So there's only one like that. You see what I mean? There's only one that satisfies both of these, you know, relations for intermediate times. And because of that, this discrete trajectory, right, actually has a continuous extension, right? And so that's where it comes from, right? And now watch what actually happens if you write this out. So we have this discrete trajectory. Well, it's continuous now, but we have it. Here it is. And what is its teeth value, right? At time t, it's the teeth iterate, okay? So you have to think about it as a teeth iterate. But that's what I mean by a teeth iterate, right there. All right? And it satisfies this equation. All right? Now, this one, right, is actually an exponential decay, right? I mean, that's what that is. And so we want to remember this in just a minute, right? But if we look at this, we can actually, because we should come up with a picture for this thing to see what this one looks like, right? So let's play with this. So what does it mean? All right. So first of all, we can write it like this, right? We can say, all right, then this is some constant, which is the initial input interval, right? And then we can say e to the natural log of 1 over 2 to the t. Right. So now, we're going to derive a differential equation for this thing, right now. And you'll see that it fits in very nice with linear search. And a third example, right? So if we know, all right, that a function is like this, you see, so we can write it like this, all right? And so we get that the measure of x of t is this. And this one is what? E to the minus t natural log of 2. All right? Now, if you remember the definition of the informatic derivative, which for any variable you have at all, right, whatever it is, okay, what do? You know, we basically differentiate in t once we measure in the variable. That's what we do. So I just write this out again, right? So x, s, like this. Then the first derivative, right here, right, is minus the natural log of 2, right, times the initial input, right, times the original thing, right, But what is this original thing? See, like that part, that actually is mu of xt. You see? And then this, a minus natural log of 2. So its second derivative then, just by like induction, right, has to actually be the natural log of 2 squared times the measure. Alright? Or if you want to put this in parentheses, it looks like this. Right? This is the differential equation, x double dot, you know, being proportional to x, where c is greater than or equal to 0. Right? Like a legitimate exponential decay. That's what this one is. Now this one over here, if we go back and look at it, we can see what its derivative is too. Its second derivative is 0. Alright? So we have an equation for linear search, right? And then right here, we have an equation for binary search, alright? And from this, by the way, we can see like what it looks like now, right? So its second derivative is positive, right? Normally we would think that means it's concave up, right? But the conventions are opposite, right? We have to remember that. And so because the first derivative is actually negative, what it means is that we should have a function when pictured looks increasing and concave down. So the graph of this one looks like this on the t less than axis. This is the graph of binary search. You see? And what's happened is when you start here, you know nothing, but then you move towards a solution and you asymptotically sort of reach it. That's what this one looks like, right? And so this one looks different. So it's a nicer picture, right? But it's still, it wouldn't validate a theory of any type, right? Well, so the one that does, and so if you want to say it, so this means that this work is like it's like an application of quantum mechanics to the idea of trying to found the mechanics of information, if that makes any sense, right? Right? It's without the quantum example I'm about to show, we would just have these straight-looking things. I mean, we have some concavity, of course, you know. And by the way, notice that this searching algorithm now actually has an initial velocity, which is very weird, and they're different, right? That's a very odd thing, and you know, so this one tends to accelerate. I mean, this is really, you know, which is something that no computer scientist would ever think of. I mean, because, you know, what do you mean the algorithm is accelerating? But, you know, it is. All right, so then the last example is quantum searching. So this is another searching algorithm. Now in this case, the simplest way that I know to model it is like this. You take finite probability distributions, all right? And all you look at is a classical state which represents the register. The order, we won't even worry about the order. There's one that's given in the paper, and it's simple. But the idea here, all right, is that the more mixed a state is, the lower it is. So the uniform distribution's at the bottom. That's where all probabilities are equal, and the vertices, or the probabilities that have a 1 in them, are at the top. And if you then look at the state of the register, which describes Grover's algorithm, you can, by pulling a very similar trick to what we did with the bisection, you get a state that looks like this. So we get the cosine squared of 2t theta plus theta. Theta is an initial angle, all right? And then we get this one. M refers to the number of solutions. So we have M of these terms, right? And then we have terms that refer to things that are not solutions, all right? So we got all of these. N is the length of the list, by the way. And so we do this. Now we have this trajectory. And again, what's really fascinating, all right, is that this trajectory also moves in a domain of states in the same way as a chain, all right? But this time, the thing that happens is that we get a legitimate example, all right? So with linear search, we saw what we get. Here's linear search in a nutshell, and what is there to say about it? You know, not much. We can say, you know, this, all right? And for binary search, We have that equation, so we'll get rid of all this, but we'll keep the equation. Because I want to make a point about this one in just a minute. So this one, and here is its picture. For quantum searching, if we use the exact same methods, right? Take the derivative with respect to an appropriately chosen variable, then we get this picture, which to a computer scientist is a stunning picture, okay? It begins here at bottom, and on the t less than axis, it moves up until it gets here, and then it moves back down. And this is a stunning picture if you're a computer scientist, because what it means is that this is an algorithm, right, where it depends how much work you do. You see, we're used to the idea in computer science that we can say, like with Newton's method or something like that. You know, if 10 iterations will solve the problem, then 20 will really solve it. It'll get us even closer, right? Or the more work we do, the closer we are to the answer. All those sorts of, you know, manifestations of non-infinity. Well, here, you can't make that statement at all. It's not true. The more you do, the closer you are to the answer. More can actually be less. And specifically, you know, if this thing right here, this magic whatever, let's call it T star, if we were to do, roughly speaking, twice the amount, we would return to a state of complete ignorance. We begin undoing the work that we originally did to get here, right? So that's the first thing, which just seeing that picture for a searching algorithm is a stunning thing. The next thing, though, we learn is that this T star, right? See, now we want to think of calculus. Well, this T star just happens to be the maximum. You know, and by the theory I talked about, we know such maxima exist. And how do we find them? Well, we can pick any variable we want, right? And we just set it equal to 0 and solve the equation, right? Now here's the funny part, right? Which variable do you pick? See, if you're a physicist, you think, oh, I pick entropy, right? Take a close look. What happens? If you pick entropy, and so you measure this trajectory with entropy, right? Then you have a bunch of x log x terms that have cosines and sine squareds embedded in them. Then you have to take the derivative and apply the product rule and all this other crap. And you will not get the answer. I mean, I'm almost positive you won't get it. I never did it, so I don't know. Right? But if instead, right, you choose a much simpler variable, and this is the variable that takes a state, takes its largest probability, takes the square root and subtracts from 1. Now, I mean, why did I choose that? Because just look up here, all right? I took the square root because I wanted to get rid of this square, because it makes derivatives harder, right? And then I did this. Now, you have to know that that is a variable in the order, right? But we happen to know that it is. If you use this one, right, and then you try to solve this equation, what equation do you get, all right? You get 1 minus the square, so you get 1 minus the cosine of 2t theta plus theta over m, right? And square root of m. And this is really easy, right? Because when you take its derivative now, you get a sine with a 2 theta out there, and you set it equal to 0 and you solve it, it's easy. That's the amazing thing. No matter what variable you pick, if you just find one variable that will solve this optimization problem, you have then implicitly solved it for all other variables, even if you can't really do the math. Like with entropy, where it just turns into a nightmare. So, to find this point in time, it just means solving this equation. I mean, it takes the derivative set equal to 0, which is easy. And it gives you this. And here's the funny part. This right here is an idealized state, but it's the state you would most want to be in if you were using Grover's algorithm. Because from this state, a measurement is likely to give you, you know, an answer to the search problem with the largest probability possible, right? And this point in time, right here, it is of the same order as the complexity of Grover's algorithm, right? You can prove that. That's discussed too in the paper. And so what does it mean? It means there's an algorithm, and you can picture it as a trajectory in an informatic space. And if you look at the point in time where the curve reaches its highest point, right, that is the complexity of the algorithm, and that is where it actually, you know, has solved it precisely. right? And so with this example here, and then these two, see, you can see now there really is a kinematics to computation. You know, in the kinematics, like I said, it refers to the mathematical description of motion, that's all. There's a deeper question here. Because if you write this thing out, here's the equation that this thing will satisfy, right? With respect to the nice variable that I just mentioned, will be like 4 theta squared 1 minus x. It'll look like this, okay? So there's your equation for quantum searching, all right? Here's the equation for binary searching, and here's the one for linear searching. The point I want to make is by making a simple change of variable that will apply to this one, right? We can make the following statement. That the class of searching algorithms has as a legitimate model. You can literally say, we're looking at differential equations of this form, okay? When C is 0, it's a linear search, right? When C is positive, the way it is here, right? It's binary searching. And if C is less than 0, all right, it's quantum searching. Now here's a really deep thing, right? That I really like. I like this part a lot. So see, we know from physics, right? You write down a spring equation for, you know, a weight attached to a spring, and it oscillates back and forth. We literally expect it to obey an equation like this, where C is less than 0. That's what we expect physically, right? Well, the quantum searching algorithm does the exact same thing, right? Because remember the picture I drew, which I just erased, it oscillates too, right? You see, you do some work, you get the answer, but if you do too much, you go back down, right? Well, if you keep working, you'll eventually go back again. You see, this algorithm is oscillating, and to a computer scientist, it's a very interesting thing. But what's really, really funny is that, I mean, it obeys the same differential equation as a spring, right? And binary search obeys the same differential equation as something that decays, like a radioactive decay. And linear search, you know, obeys, you know, that equation. It doesn't accelerate. And so you can actually take now this model, and you can actually completely reverse your thought process and say, wait a minute, what if we just decided to believe that there is an informatic universe, and within this informatic universe, there is such a thing as mechanics, right? And that instead of taking our fundamental things, we just took these equations. And we went, the phenomena we're talking about are these equations, right? Then the question you would want to ask about next, to have a full-fledged mechanics of information, would be the question of a dynamics, right? There are 3 differential equations. That's how they arise. I put this in quotes, because it's not force, but it's the sum of something, right? The sum of something should be proportional to the acceleration. And that's the question now, basically. What are the analogs of Newton's laws that will let you derive these differential equations for processes like these? That's the search for genuine mechanics of information. That's what the paper asks about, you know? Yeah. Are there any questions? No, I'm just kidding. Yeah.